Okay. Well, it looks like we've got a couple people here already. We'll just maybe get started. So, Michał, feel free to share your screen and I'll turn it over to you.
All right, so let's start then. So hello everyone, once again, my name is Michał Zaczański. I'm a cloud software architect at Intel, based in Poland. And my work is focused around caching, around storage caching, including Opencast. And this is the topic that I want to show you today. What Opencast is, what are the features, maybe it could be interesting for you. And if you have any questions, feel free to interrupt me at any time. All right, so quick agenda. So first I will do very high-level Opencast overview. I will talk what Opencast is, how it can be used. Then I will go through the features from user or administrator standpoint. And finally, I will do quick intro of Opencast architecture, a bit of technical details, but not too much this time. All right, so let's start what Opencast is. Okay, I think this window. So Opencast stands for Cache Acceleration Software. The idea is pretty simple. It's a caching software, storage caching software for Linux that works in a block layer. If you are familiar with DM cache or Bcache, then Opencast is something similar. So as I said, idea is simple, cache slower media on faster media, just to accelerate the storage. So Opencast, comparing to other caching solution, has some unique features that I will go through them on later slides. It's also optimized for fast SSDs. During couple of recent releases, development team did some improvements to reduce the latency, improve the throughput and bandwidth of the software. It's free and open source, available on GitHub, and it's also kind of portable. I will go into the details what this kind of portable means, but it's not tied to specific platform or storage stack. All right, let me switch to the next slide. So Opencast for Linux kernel, what is it? What it contains? So it's a block driver, kernel module for block driver. Currently we support kernels up to 5.12, but we recently regularly add a new feature support for newer kernels. It's managed through command line utilities. We have integration with system boot scripts like udef and systemd, and of course there's also documentation available. And just to show you how it fits into the system, here is a very, very quick start for a very simple scenario. So first you need to select a fast block device to be used as a cache media. It should be SSD, preferably NVMe. And you start the cache instance using this block device. Then you attach a backend device to that cache instance. You can attach one or more. In this example, it's just the one. And then you can start using your storage through Opencast. The important thing to note here is that you don't need to provision a backend device in any way. You can take your existing, let's say, HDD with data attached to Opencast, and all your data would still be there, could be still accessed. There is no data loss during this procedure. After you finish that quick startup, quick configuration, all your data would be visible through new block device like CAS1-1. And as you can see on the screenshots here from LSBLK, the CAS1-1 is just a view on the SDC, but all the traffic would be routed through CAS driver, and this driver will decide where to put or from where to get the data, from either backend or from cache device. Sorry. The previous example was very simple. It was a typical one-by-one configuration when you use single cache device to accelerate a single backend device. But with Opencast, you can have more complex configuration. I mean one-to-many configuration, in which case you use a single cache device to accelerate multiple backend devices. And in this case, the cache is shared. So if there is a need for more cache for one backend device, it can be borrowed from another one. It's simple one cache area to accelerate multiple hard drives or multiple other type of backends. It's also possible to stack one cache instance on top of another. I don't have this on the slide, but CAS devices, I mean those CAS 1-1 or 1-2, are regular block devices. So they can be used as input for another cache instance. So for example, you can have very, very fast cache on the very top, and you can use that very fast device to accelerate another cache instance that uses slower cache device. And you have kind of tree of cache instances. And as I mentioned, it's fully transparent. There's no data loss on the backend devices. How it fits into Ceph then? So if Opencast exposes regular block devices, then you can simply deploy OSD on top of that device instead of deploying it directly on hard drive. You need to configure the cache instances and then start to use those exposed virtual devices instead of original ones. And there are two possibilities. Again, the first picture is for one-on-one, and the second one is for one-to-many deployments. In the first one, you simply create separate cache instance for each OSD, while on the second one, you share the cache. Both approaches have pros and cons, but while in the Ceph, the traffic across OSDs should be more or less evenly distributed, the better choice seems to be to use one-to-one deployment. Because cache metadata is not shared, it would have some performance optimization then. Shared cache is more for cases where traffic between backend devices is not distributed evenly. All right. So any questions to this quick overview of what Opencast is and how to use it?
So you're mentioning that there's no data loss. Does that mean this is a write-through cache and CAS is only doing read acceleration?
No, we have 4 more than one caching modes. We have write through, we have write back, by data loss at this point, I mean that when you start new cache instance, you don't need to do some kind of provisioning on the backend. So you can take existing block device with existing data, plug it into Opencast instance, and you will still have access to this data through Opencast instance.
Okay, but I mean, once you start running it, then it's going to flush out in whatever order it wants to the backend device, right? Yeah. Okay.
Yeah. Okay, so let's get to Opencast features. What Opencast can offer you? So, cache modes. Cache modes are the simplest features that each caching software should have. So we currently have 4 caching modes. The write-through, it's probably the simplest one. In this case, your data is always in sync between cache and the backend storage. And because of that, it accelerates only reads. Writes are always targeted to both cache and backend storage, so there is no acceleration to writes. For the write back, both reads and writes are accelerated, but in this case, some data might be out of sync between cache and backend storage. So in case you want to stop cache instance, you should first flash the dirt data, the data that is out of sync with backend storage, and then you can safely detach backend device from cache instance. There is also background flashing, background synchronization. That I will cover on the next slides. We also have a write-only mode, which should be rather called write buffer mode. The difference between write back and write-only is that in write back mode, the data is inserted into the cache on both reads and write requests. While on write-only cache mode, we insert data into cache only when handling write requests. Read requests are handled in pass-through mode, as they are handled directly from backend storage. Of course, assuming that data for given LBA is not in the cache already. In case it's in the cache, we of course return data from the cache because it's the recent one. And the write around, in this write around accelerates also only reads. So in this manner, it's similar to write through. And the difference is that data is inserted into cache only during read handling. Writes are targeted directly to the backend storage. So it's kind of opposite to write only. All right, we also have a pass-through cache mode. I didn't put it here because it's not a really caching mode. The pass-through mode is just to temporarily disable caching. In pass-through mode, everything goes directly to the storage, to the backend storage. All right, so cleaning or flashing policies. It applies to the write-only and write-back cache modes because flashing is responsible for synchronizing data between cache and the backend storage. In Opencast, flashing happens in 2 different ways. You can force Opencast to flash all the data manually by using command line utility. But also Opencast flashes dirty data in the background. And this background flashing is controlled by cleaning policy. So currently we have 2 cleaning policies, although there are 3 on this slide, because the last one is no background flashing, so it's like no cleaning policy. ALRU, this policy is simply based on access time on LRU list. So least recently accessed blocks are flashed to the backend storage. The second one is ACP cleaning policy, which stands for aggressive cleaning policy, which is best for HDDs because this flashing policy tries to sequentialize data as much as possible. So it simply selects the most dirty region in LBA domain in the cache and flashes that first. So it divides the whole LBA range of backend device into some chunks, then flashes those chunks in the order of percentage of dirt. So there is highest probability to form some sequential regions. And NOP, it disables background flashing, as I mentioned. All right, promotion policies. You can also configure how do you want to insert data into the cache. By default, given LBA block is inserted into the cache if it's not yet in the cache on the first access. So first touch of the given LBA would insert that data into the cache. But it's not always best strategy because there might be cases that you have some important data in cache, but from time to time there happens very random traffic that just touches the blocks, and those blocks are never used again. So for that we have nhit promotion policy, which inserts data into the cache only when given LBA or given block was accessed more than specific number of times in some time window. You can configure how many times this block should be accessed in order to be inserted into the cache. Okay, selective and priority-based caching. This is probably most interesting feature of Opencast, which gives you opportunity to cache only the data that you know that is suitable for caching and only the data that you want to accelerate most. So you can configure Opencast using various attributes or various classification rules and assign priorities for given classes, or even tell Opencast not to cache given class at all. So, for example, you can classify data based on request size, LBA ranges. If you are using file system, then you can classify based on some file system related attributes like file name, directory, file sizes, and some process related things like PID or process name. And also recently we added support for write lifetime hint, which is available on kernels starting from 4.12 or 18, I don't remember exactly, and is supported, for example, by RocksDB. It simply allows user space application to specify some priority of data. Expected lifetime of given file or LBA, and we can utilize this write lifetime hint in Opencast to, for example, put data that is expected not to be touched for a long time, static data, directly on the backend storage, while very dynamic data that is very often overwritten to put it into the cache with the highest priority.
And sorry.
Yep.
You said, I think you said that you are able to say which I don't know, file name directory will not be out of the cache? Can you also say which the only one that will be in the cache and all the others would be out of the cache? So there's one directory you want to be cached and all the rest are not?
Yes, you can build those are attributes that you can use, but based on those attributes, you can build some classification rules. So, for example, you can say that you want to cache directory A, directory B, directory C, directory D, but you don't want to cache anything else. Or you can say that you want to you don't want to cache directory A, B, C, and D, but want to cache everything else. You can assign different priorities for each directory. You can specify the directory A is more important for you, so you assign priority 1 to it. Directory B is a priority 2, and so on, so on, so on. You can even use some logic operations and combine those attributes together. So you might want to cache, for example, all files that are smaller than, let's say, 40 kilobytes that are placed in directory A. Does it answer your question?
Yeah, yes, absolutely. Thanks.
Okay, more details on that, because this is a bit complex topic, you can find in our documentation on GitHub. Here's a link, so you can look at it into more details, for more details. All right, sequential cutoff. Sequential streams are usually not very good for caching because they can quickly pollute your cache, evicting random data. So Opencast has a feature that we call sequential cutoff that allows you to track sequential streams and avoid caching it. And you can configure when the sequential cutoff should be triggered. We have 3 options, actually. The one is that you want sequential cutoff to be active only when your cache is full. The second option is that you want to have sequential cutoff always, even you have a lot of free space in the cache. And the last one is to disable sequential cutoff at all. And you can also configure the minimum size of such sequential streams. So it means that you can configure how much sequential data should be sent to given block device in order to be treated as a sequential stream. And we can track multiple sequential streams that way. So if you have multiple applications writing to the same block device, and those, yep.
Why would, I mean, you would never want to cache a written sequential stream. I was thinking about reading. So, all right.
It applies also for reading. Might
reading, you might want to prefetch, right? I mean, so you need to recognize them, and so it sounds like you've got that, and then you can make decisions.
Yeah, you might prefetch, but if sequential stream is large, then it would evict your data that might be more important to have in the cache, some random data, for example.
Right. Yeah. No, I've just worked with scenarios where you, once you recognize a sequential read pattern, you prefetch, but you also, your eviction strategy has to get rid of the old data quickly. But you don't. Doesn't sound like you have that.
Mm-hmm. Yeah.
Okay.
All right. Okay, let's get to the next one. And manageability. As I said at the very beginning, Opencast could be controlled using command line utility, but this is good if you want just to play with Opencast, to test it. But in production environment, it's not very friendly method to use. So we have a configuration file that you can use, that you can dump your whole cache layout, and then system startup scripts would would rebuild the cache configuration on the startup. And we also provide statistics for cache to monitor the cache. We have about 30 counters to monitor cache, how cache is used, by what kind of data. We collect that counters at different levels. You can query for statistics at the whole cache instance level. You can query at the single backend device level if you are caching multiple devices using single cache device, or you can check statistics at the IO class level if you are using IO classification. And you can either output it on the screen using human readable format in the format of some tables, or you can export it to CSV file for some machine processing. All right, any questions to features part? Okay, so let's get a bit.
Yeah.
Yep.
Just regarding the IO classification, so it's covering file data, and just from the description, it says it discovers metadata and data. Is there a specific file system meant to be used for that, or what is the catch here?
It works for XFS and ext based file systems, so ext3, ext4.
Okay, thanks.
Yep. All right, so let's get a bit into more technical details, a bit into architecture. So how Opencast organizes its cache space. So as typical cache, we divide cache space into cache lines. You can configure what cache line size should Opencast use, and we support 4K, from 4K to 64K with powers of 2-step. And it is important to select optimal cache line size, because all the caching operations we are performing, like mapping, eviction, thrashing, we perform with cache line granularity. So if cache line is, for example, 64K, it means that 64K of cache is mapped into 64K continuous space of a backend storage. But we also track validity and dirty with a granularity of 512 byte sectors. So it means that you might have 64K mapped to 64K region on the backend, but you might have only some part of that valid into the cache line. We don't perform any padding or prefetch. So for example, if you request, if you have 64K cache line and you request 4K of data, you send 4K request, then we would read only 4K data from the backend and put that 4K into the cache. Even the whole 64K is mapped for the 64K region on the backend. It prevents from increasing the bandwidth to the backend device, and it's also important during flashing. So we flash only the dirty sectors. So if you have 4K cache line, for example, and only one sector, one 512 byte sector is dirty in that cache line, we would flash only 512 bytes, not the full the cache line. So we would avoid write amplification factor. And because of that, it is important to set the correct cache line size. Because if your cache line size would be too large, you might end up with suboptimal cache utilization. Like in this example, you can see that this is a 4K cache line size example, the smallest one, but you see that some sectors are mapped but invalid. It means that data for those sectors were never requested. So cache allocation is currently 30% because 3 of 10 cache lines are mapped, but utilization is only 20%. Only 20% contains valid data in the cache. And if your workload is, for example, 4K random workload, and you set 64K cache line size, then your effective cache utilization would be 1/16 of your cache size. On the other hand, if your workload is your average request size for your workload is, let's say, 64K, and you set 40K cache line size, nothing bad happens. Your cache would be utilized perfectly, but Opencast would need to track more cache lines than it's necessary. So it means it would consume more DRAM for metadata, and it would consume more CPU cycles to do the caching logic. So the optimal configuration would be to match your average request size with your cache line size. All right. So how Opencast looks, how Opencast architecture. Okay, are there any questions to this cache space organization before I go to the next one? Okay. So how Opencast architecture looks from the very high level. At the very beginning, I said that Opencast is kind of portable. It's because our whole caching logic is contained in a caching library that we call Opencast Framework, which is platform independent. And currently, we have two CAS products. One is an Opencast for Linux, which is Opencast for Linux kernel, which I mostly described in this presentation. We also have Opencast for SPDK. It's the same caching framework, the same caching library, but integrated with two different environments. One is with Linux kernel, another one is with SPDK. You can also integrate Opencast Framework with any other environment, assuming it's a block-oriented storage stack, because Opencast Framework is a block-oriented caching storage. In order to integrate it with some stack, you need to wrap Opencast Framework into either driver or in your application and provide a top adapter and bottom adapter. The top adapter is a layer on top of Opencast Framework, which is responsible for accepting requests from the storage stack. So it needs to understand how given storage stack sends the requests. In kernel, it would be bio-based. In SPDK, it would be BDEF layer. And this top adapter then sends, it translates the request from the platform-specific structures into Opencast Framework structures. There is no data copy, only the IO request description is transformed. We don't copy data. Data is always in the buffers that application or upper layers sends to us. On the other hand, there's a bottom adapter, which is responsible for sending requests to cache and a backend device. Whenever Opencast Framework wants to perform some IOs, and it has to perform some IOs, it has to put data into the cache, get from the backend storage, and so on. Opencast Framework doesn't perform it directly because it doesn't know how to do that. Instead of that, it uses API, a common API with bottom adapter, and the bottom adapter translates CAS requests into the platform stack requests. And two examples how it works. I partially already described that. On the left hand, you have architecture for Opencast for Linux kernel. On the right hand, it's for SPDK. So top adapter, which is part of Opencast kernel driver, accepts from requests from block layer in the Linux kernel, translates it into Opencast Framework requests. Opencast Framework performs all the caching logic, decides where to put data, what to do with the data, and so on. And finally, it asks bottom adapter to put data on the devices. And bottom adapter communicates with a block layer, which is a device driver layer, and data goes to physical hardware. Similarly, for Opencast for SPDK, there's a BDEF layer on top, which translates the BDEF type requests into OCF requests. Opencast performs all the logic, and finally, bottom adapter uses other BDEFs from SPDK to write data or read data from cache and or backend device. Any questions? All right. So what is in Opencast Framework? Basically everything that cache software, storage cache software needs. So caching engines, support for I/O classification, cache partitioning, eviction policies, promotion, all the policies that we have, eviction, promotion, and cleaning, the background cleaner implementation, metadata handling, statistics are also collected in and managed inside Opencast Framework, and API for management. And all these items are exposed from Opencast Framework through API. So the CAS integrations like top adapter and bottom adapter can query or can manage Opencast Framework through that API. And I think, yeah, this is the last slide that I had. So any questions?
How, out of curiosity, I know that there was some concern about showing direct benchmarks, but in the past, it's looked like you guys have seen some advantage by the way that you handle your promotion and evictions. Can you talk a little bit about that compared to just generically other solutions?
Yeah, sure. It's mostly related to that cache space organization. We compared this with DM cache, and we found that DM cache, especially for lower request sizes, generates very high write amplification and read amplification. It's because DM cache organizes its data in chunks, but those chunks are much larger. I don't remember the minimum chunk size for DM cache, if it's 32K or higher, but it's not that important. More important is that when you, for example, read or write data that is you send request that is smaller than the chunk size, DM cache needs to, DM cache does not track validity of each sector. So if you read just 4K and you have 32K chunk size on the Mcache, it would read the whole 32K. So if your workload is random, then your read amplification in this case would be 32K divided by 4K, so it would be 8 times. So it would generate 8 times higher traffic to backend than your workload. And while for reads it's not that bad, it's more important for writes, especially if you are using SSD drives, DLC or even QLC, because the same happens when data is flashed. If you write with small request sizes, flashing on the Mcache would still happen with chunk size. So only if 4K would be dirty, the whole 32K of data would be flashed to the backend storage, which would generate write amplification, which is more harmful for SSD devices. So this is basically the difference, the main difference that we found.
One of the things I remember when looking at DM cache is that there was a maximum number of chunks as well. I believe if you exceeded that, then your chunk size was automatically incremented by 2. So I don't remember what it was, maybe 1 million chunks or something like that, and then your chunk size was automatically increased. Do you recall that? Was that correct? Am I thinking about that right?
Yeah, there is a limit for chunks, so you have to choose. If you have a big cache, you need to choose the smallest possible chunk size that meets that requirement. So even if the minimum chunk size is 32K, that limit might force you to use, let's say, 64K or 120K, 28K chunk size, which would further increase the write and read amplification.
Yeah, sorry, go ahead.
In Opencast, there is also a limit for cache lines, but we track cache lines with 32-bit integer, so it's a much higher number than 1 million.
Excellent. And do you see that if you have a lot of chunks, then does that cause slowdown or dramatically increase memory consumption, or is that a problem?
Memory consumption is directly dependent on your cache size, so on number of chunks. So this is why I mentioned that you should match your cache line size with your average request size, because if you choose too small cache line size, then you would consume more DRAM than is really required. Actually, Opencast DRAM consumption for Linux kernel version is 2% of cache space, of cache device size for the smallest cache line, for 4K cache line. And for larger cache lines, it's you should just divide it by 2, 4, and so on.
When you've tested your Ceph with Opencast, what cache line size do you use?
We typically test it with 64 cache line, with the highest possible. But if we want to use small request workload 4K, then we also use 4K. It depends on the scenario. You should choose that depending on your typical use cases. Okay, any other questions?
Do you have any results from the benchmarking you've done with Ceph?
We are in progress. We are doing some benchmarking right now. We have some preliminary, but they are not at that point to present. But we are doing extensive benchmarking right now, so we should have some data soon.
Michał, there was some benchmarking that was done versus DM Cache maybe 5 or 6 months ago. Are those results something that we can eventually share with the community, or would those be still governed by NDA?
Let me check that. I don't have those results right now, but let's check and we can potentially follow on some next meetings.
Okay.
All right.
Cool. Well, thank you so much.
No more questions. Thank you very much.
Yeah, thank you, Michał. Thank you for presenting. This was really interesting. Yeah, definitely would be really interesting to see some of those earlier results or the new results that you guys have been working on, especially with hard drives.
Yep.
So yeah, would absolutely be interested in having you guys do a follow up. Well, thank you very much.
Welcome.
I don't have anything else for people. So does anyone have anything for the last 10 minutes that they want to bring up or talk about before we wrap up? All right. Well, then, thank you, Michał, and thanks everyone for coming. Have a great week, and we'll see you next week.
Thank you. Have a good day and good weekend. Bye-bye.
Thanks.
Bye, everyone.
Thanks a lot. Bye-bye.